Hello students, welcome back. Let us resume our discussion in section 1. Previously we studied symmetric groups, basically the groups of all finite permutations. Now let's go to the next topic, dihedral groups. A dihedral group is a subgroup of a symmetric group that consists of 2D concentric congruence maps only. Here's a visualization. Let's suppose we have a necklace with 8 balls. Numbered balls from 0 to 7 like this, and instead of 1 to 8, I'm using 0 to 7 here for some geometrical simplicity and also connection to Z8. Let's start from 0 to 7 like this, and then it's a necklace, so we can turn it around. So if I turn it once and then twice, then 0 will come here, thrice and 0 will come there, and 4 times 0 will come down here, and then we have same order. And then you can flip. And then we can repeat it any number of times in any order, and you're gonna get some congruence maps. And we have symmetry only in 2D. And this kind of group is called a dihedral group. And one way to visualize is, this is a visualization, the picture here, blue and red, rotation and inversion. Rotation is represented as Greek letter rho typically, and inversion, flipping, typically we use Greek letter tau. And then please note the natural connection to Z8. In general, Zn, but in this case, Z8. So start from 0, 1, 2, 3, all the way to 7 bar, and then consider k to k plus 1. So 0 goes to 1's place, 1 goes to 2's place, 2 will go to 3's place, and so on. So it's basically k bar to k plus 1 bar. And that being repeated many times. We can repeat it up to 7 times actually. And then that corresponds to the rotation. And then you can flip around. So k going to negative k, or equivalently n minus k, because n is equal to 0 modulo n. In this case, n is 8. Now this program is randomized, so if you run it again, you're going to get something different. Yeah, initialize all the time. In this case, n is 4. Too simple. N is 10. Okay, all right. So we have colored balls or numbered balls from 1 to 9 and form a necklace. And then you have one rotation. And then you're looking at a flipping. So an arbitrary element will look like this. So any number of rotation many times, and then any number of flipping many times. But then again, this tau, if you flip twice, you're going to come back to original place again. This is just flipping, so flip twice and then you're going to come back. K go to negative k, and negative negative is original. And this one here, if you repeat it n times, then you're going to come back to the original. So this r and t values are not really that outrageous. So even though theoretically you can get really large powers here as r and t values, in practice they're bounded. And the repetition that can be reduced too, as a matter of fact. And this kind of group is called dihedral groups. A dihedral group is non-abelian in general. And here's a visualization. Tau times rho is not the same as rho times tau in general. Here we have visualization of rho times tau. So tau first, flip first, and then rotate. So flip, so 1 goes to the here, 2 goes here like that. So we have inverse orientation. And then rotate 0, 1, 2, 3, starting from 0 in previously one's place in original place and then goes around clockwise. Now if you do rho first and then tau later, you're going to get something different. Rotate first, so 0 comes here, and then we have counterclockwise orientation, and then flip it. So 0 goes over here to the right, and then as you see, it's different. You have clockwise orientation as before. Clockwise orientation is before, but starting number 0 is different. 0 is in original 1's place. Here, 0 is in 5's place. They're different. So this is non-abelian, but as a matter of fact, they may be different, but not outrageously different. They may not be commutative, but they exhibit something called anti-commutativity. So tau rho is rho inverse tau, or equivalently rho tau is tau rho inverse. Can you prove the equivalence? From here, if you multiply tau to both left-hand side and right-hand side here, what happens? Tau times tau, well, tau times tau is identity. Let's go back here. Tau is just flipping. Flip once and flip twice, you get back to the original. So tau is actually tau inverse. So that's just identity, so we get that. And then we multiply tau to right-hand side. The same thing. Tau times tau, they just disappear. That becomes identity. And that's what we have over here. So these two are actually equivalent. So tau rho is rho inverse tau. Rho tau is tau rho inverse. But then again, is this really true? And yes. Here's the visualization. 0, 1, 2, 3, 4. Yes, we have this original. And then let's flip it first. So tau first. So 1, 2, 3, 4, like this. 0 stay the same, but reverse orientation. And then take the rotation. 0 comes here in 1's place, and then we have reverse orientation, clockwise direction. Algebraically, we can write like this. In Zn, k bar goes to negative k bar, that's flipping, and then plus 1, that's rotation. So negative k plus 1 bar. And then this one is tau rho inverse. So from here, rho inverse. So instead of taking one rotation counterclockwise, we take one rotation clockwise. So 0 goes here in 8's place. And then we flip. 0 comes here, and then we have reverse orientation, so it's the same. So here, this blue and this red, please check, they're the same. Please compare, they're the same. So tau first and then rho versus rho inverse first and then tau, they're the same. And this is for z equals to 9, n equals to 9, so we have z9, but this program is randomized, so run it again and you're going to get some different n value. They're all going to be the same. As a result, the arbitrary element doesn't have to be this complicated. You can reduce it further, change this order. Each time I change, I get negative, and then combine rows, and then do whatever repetition. So you're going to end up with these. Tau to the t power, rho to the r power only. And r is going to go from 0 to n minus 1, because if you take n rotation, then you're going to get back to the original. And the tau will go only 0 or 1. No flipping or just one flipping. 2 flipping, then you're going to come back to the original. As a consequence, the order of the dihedral group is 2n. Here's an example problem from the textbook, and I'm going to leave the majority of the computation to you. Determine the subgroup structure of the dihedral group D4, and here are all the elements of D4, and that's what I got from the textbook. And you can check manually. So 1, 2, 3, 4 become 2, 3, 4, 1. What do you see? Just a shifting, right? Just a rotation. And then 1 plus 1 is 2. 2 plus 3 is 3. 3 plus 1 is 4. 4 plus 1 is 5, but equivalent to 1 modulo 5. And 4 is actually, it is better to use 0 instead of 4 if you use this mod 4 operation. And that's the convention I used before in my visualization. But here in our textbook's way, we use 1, 2, 3, 4 instead. But remember, 4 is equivalent to 0. And then plus 1 again, and what you see? You have a 4 cycle. And then if you take this first column only, bigger font is not really generating easier view because this is a picture file. So let's come back to the original size. If you take the first column here, then you're going to get a cyclic group of order 4. And then this mu1, mu2, and delta 1, delta 2 are all 2 cycles. Oh, excuse me, they are not 2 cycles. Sorry about that. Mu1 switches around 1 and 2, and then 3 and 4. And mu2 switches 1 and 4 and 2 and 3. And then delta 1 and delta 2, those are 2 cycles or transpositions. They mean the same thing. 2 and 4 stay the same and switch 1 and 3. And delta 2, let's see, 1 and 3 stay the same and switch 2 and 4. I guess that's it. And what if you keep, say, 3 and 4 and switch 1 and 2, for example? That belongs to a symmetric group, but not on the dihedral group. If you draw a picture, you will see it. And I think there's a program here. So let's see. Let me run this program until I hit n equals to 4. Okay, I got n equals to 4. So 0, 1, 2, 3. So if I flip, I can flip with respect to vertical axis. So I can flip 1 and 3. Or I can flip with respect to horizontal axis, and I can flip 0 and 2. And I can flip diagonal axis, so flip 0 and 3 and 1 and 2. And with respect to the other, flip 0 and 1 and 2 and 3. But I cannot flip 0 and 1, leaving 2 and 3 as the same place. You see? This is basically 2D dynamics, so the visualization is relatively easy. If this is a necklace, there's no way I can keep 2 and 3 and switch just 0 and 1 unless I cut this cord and then get those balls out and then reproduce this necklace. So we have all those elements there, and then with respect to those, we can form a group operation table like this. It's going to be horrendous computation. I'm going to leave that to you. I'm not going to even start. And then the subgroup structure, again, computation heavy, so I'll just leave that to you.